Hello, everybody. Some of you might have seen me give a talk about microstates at React Toronto meetup. How many people were there when I gave a talk about microstates? No, one person? Awesome. All right, cool. Well, so it's cool because talking about microstates is a little tricky. It's 2 years of work that we're presenting now. There's a lot of ideas that are a little bit like different, and so this talk could be 3 talks. So it's probably going to be one of a series of 3. I need to like keep condensing stuff, but I'll just get started. So where we're going to go with this first is that, we'll start with this idea that, thank you. We'll start with this idea that our data types have intrinsic operations. So if you think about this, like how many people know how to increment a number? You know, everybody, right? I mean, this is like, you know, we do this all the time. Like mobx, you increment a number. Oh, sorry, Redux, you increment a number. Mobx, you increment a number. Set state, you know, you can increment a number. Unstated, you can increment a number. You know, the funny thing is that incrementing a number is an operation that is intrinsic to the number. So it's kind of funny that we have to keep implementing the same thing over and over again when, in theory, how to increment a number should actually be part of the number itself. We should be able to increment a number without having to write the implementation for incrementing a number. And the same thing happens with most of our JavaScript data types. You know, we should be able to, for example, toggle a Boolean without having to write how to toggle a Boolean. We should be able to implement how to do an immutable push into an array without having to, you know, do the spread operator and actually like, you know, manually write how you would actually perform that operation. Because in many ways, when we do the manual work of performing operations that are intrinsic to the data type, we're actually doing computer's work for the computer. And we should be able to just say, like, I have a number and I want to increment it. You know, I have a Boolean and I want to toggle it. I have an array of to-dos and I want to push a to-do into it. And what you should get is a new array that has that operation. That has that to-do item pushed into it. And the thing is that it's not hard. Like this particular, like doing this is not difficult. But we shouldn't have to do this because it gets difficult really fast. So my name is Mankovski. I'm a software engineer at Frontside. I'm a JavaScript mentor as well. Frontside builds JavaScript platforms. And what I want to talk to you about is I'm going to continue this conversation about the kind of the fundamental building blocks of state management. And these basic JavaScript data types are exactly that. Our applications are built out of hundreds and hundreds of these values that have intrinsic operations that you can perform on them. And this gets complicated because you start off with having like, you know, a true or false value, like a Boolean complete value, and then that very quickly becomes like it becomes part of a to-do. So now you have a to-do item that has a complete status, and then that to-do item becomes an array of to-do items that have a complete status. And now you have these 3 levels of you have these 3 operations that are kind of compounded together. You have this to-do, toggling the status of the Boolean. If you want to perform an operation, you need to figure out how to do that on a new to-do item. And then if you want to update it inside of an array, you need to figure out how to do that on the side of an array. So if you were to toggle a to-do inside of a, if you want to toggle a status on a to-do item that's in an array of to-dos, this is how you would do it with Redux. The challenge is that when you look at that, if it wasn't for the complete to-do, you probably wouldn't know what's actually happening there. It's very difficult to deduce what is the actual intent of this block of code. And the challenge here is that this complexity just compounds, just keeps spiraling. The complexity of performing operations on composed data types just get harder and harder with every level of complexity. And so what happens is that we end up managing all this complexity in our minds. And we manage all this complexity in our code. And so the work that I started doing started was that it started from this idea, like, this should be easy. Working with state in JavaScript applications should be easy. And working with types in JavaScript should be easy. And so if you're like hip and you use cool things, you probably like, what about TypeScript? Like, TypeScript is a system designed for managing types in JavaScript, right? So the challenge is that TypeScript it's a build-time tool. All it will do is it doesn't produce anything in the runtime. Like, it generates JavaScript, but it doesn't give you anything. It doesn't make toggling a property particularly easier. All it will do is it'll just say it doesn't have toggle. It will just tell you that you can perform that this thing is a Boolean, and then you can do something with that Boolean. And if you didn't do something, if you didn't do the right operation on that Boolean, you're doing something wrong. So it will tell you that you're working with the wrong data type, but it's not actually going to make it easier for you to work with that data type in runtime. And so what Microstates is, it's a runtime type system that's designed for composable JavaScript. It's designed to compose JavaScript state. And one of the kind of basic things that Microstates comes with is it comes with some common operations that you can perform on basic types. So like, what you can do is you can create a Boolean. You can create an object that represents a Boolean, and then you can invoke toggle on it. So Microstates will give you a toggle transition that will give you the inverse of the toggle. It will give you a new object that represents the inverse of the original value. And Microstates will give you the same thing. It'll give you a number object that has increment method that you can call, and what you will get is another object that represents the number, but it's been incremented by 1. And you can do the same thing with array. You can create a microstate that represents an array. You can give it some value, and you can push a value into that array. And what you're going to get is a new object that has that value pushed into that array. And also, Microstates also supports like object strings, and then any, which is like any value can become. You can set any value into that placeholder. Now, going back to this idea is that this is not hard. Like so far what I've described is actually it's not that groundbreaking because, but it is laying the foundation for doing more complicated things, and we need to do this because doing this becomes hard very quickly. One of the challenges with managing state is that typically what happens is that if you don't have a way to manage complexity, it starts to compound very quickly. You add one state value, then you add another, and then you have to reset the other one. When you set the first one, and like the complexity around managing state becomes very high, very fast. And so what we want to do is we want to lower that curve. We want to make it cheaper, less expensive to add state to your application and be able to perform operations in that state without it becoming something that becomes more difficult over time. And ultimately what we want to do is we want to let computers do the work for us. We want to leverage the computer's ability to understand complicated things and work for us so we don't have to work for it. So the question is, how do we do this? How do we lower the complexity curve when working with types and composing objects in JavaScript? So we're going to flex our thinking muscle for a bit, and we're gonna start off with this idea that types are trees. So what I mean by that is that you can represent a type as a tree. So I'll give you an example of this. So if you look at this person type, this person type has two properties, and these two properties, like age, which is a number, and name, which is a string, you can kind of look at them as a tree, as this, the object that I have on the right. And so the cool thing about trees is that trees give us branches, and branches are paths. So we now have, by representing a type as a tree, we now have paths. We can point at a specific thing in a tree and say, this thing, I can point at that and say, like, I can access that thing at that particular path. So in this case, if I wanted to access a number on a person object, I can point, if I want to access the age, I could just do, in this case, it would be person.age. And now I can perform an operation that's intrinsic to that type at that particular location. So I can call increment. And what this will do in microstates is that you're going to get a new object. So this older is going to be a new person object where the value of age is incremented in that particular place in the object. So now Microstates is handling for you, doing immutable transitions and creating immutable object for you. And all you have to do is just define the structure of this data using a type system, just a regular JavaScript class. So this combination of paths and type transitions gives us the ability to invoke transitions anywhere. And this is kind of the first kind of fundamental, these two pieces together are fundamental building blocks of being able to build complex state data structures without having to jump through hoops of actually managing that complexity. So if you wanted to compare what that would look like, you could take this example from completing a to-do in to-do MVC app in Redux. This is taken from Redux to-do MVC app example, and you could, what you have at the top is what we started with, which is we're manually toggling the to-do status, and what we have with microstates is a very direct representation of your intent. I want to go into my to-do MVC object. I want to reach into the to-do property at the first object, or object at the first index 1. I want to take that object. I want to take the completed state, and I want to toggle that state. And what you're going to get is you're going to get a new to-do MVC object where the value of completed has been toggled in that particular location. So you have now, so Microstates has done for you is it's completely taking care of figuring out exactly how to create everything as a result of making change in that one particular place in the tree. So this is one of the things that's really kind of fundamental. I mean, it took us. It was something we started with kind of by accident, but it's proved to be extremely powerful. It's the idea that anytime that you invoke a transition anywhere in the tree, what you get back is a new object at the root of that microstate. And so what this does, it allows us to, it gives us a way to work with these complex objects in a very predictable manner. But this intrinsic nature, the nature of types having intrinsic transitions that you can perform on them, kind of goes a long way. Because, for example, you might have, like, if you wanted to represent a person, something that a person can do is a person can start walking. So that operation of walking is actually part of the data type. So it's actually helpful to be able to define. There's kind of two things two ways of looking at this. One is the things that you can do to that object define that type. So the fact that a person can walk and a baby can't walk, like that actually is definitive of the different types of entities that we have that we can model. And so it is helpful to be able to create create types that have their own custom transitions. So not just primitive types that have their intrinsic transitions, but you should also be able to say, for this data type that represents certain kind of data in my application, I want to create a special transition that is going to be appropriate for that data type. So if you look at like a modal can have a few composed properties. So you could have a composed microstate, so is open to indicate whether the modal is open or not. Then you have a title, and then you can describe a transition that you can perform on that modal, which is intrinsic to the modal, and it goes along with the actual data type. So one of the things that's part of the design of microstates and the whole idea of reducing complexity is that it needs to be predictable. So, and it needs to have as few concepts as possible. So there has to be patterns of repetition that go through over and over again through the API, so you know how it's going to behave. So one of the things, for example, is that you can invoke transitions you can invoke transitions on the outside of a microstate, but you can also invoke transitions inside of a microstate, and you can chain those together. So you can perform multiple transitions in one operation. So you could see here what we're doing is we're chaining. We're starting off by setting is open to true, and then we're chaining to it, applying the title set to the title value. So you can, and then this API, chaining API, available both inside of the microstate and it's available outside of the microstate as well. And this is a really important design quality. There is something that is also important about this, which is that maybe I might have a slide about this later. I'll just go on. So one of the really interesting things about the way that transitions are designed in microstates is that transitions can change the node that they operate on, the microstate that they operate on. They can change its state, they can change its value in an immutable way, meaning that when you invoke a transition, you're going to get a new object that has different values. But it can also change the type of object itself. So you can actually replace the node with a different node, and that node will have different transitions. You'll have different properties. So the object can actually replace itself with a different kind of object. And you can see that here, which is, so if we were to represent authentication as a microstate, what you could have is you could have an authenticate transition, which takes a user, and then what it will do is when you invoke this authenticate transition, that node where you invoke that transition is going to be replaced with a type that is authenticated session as opposed to an anonymous session. So this is kind of what that would look like. So if you start up with an app, and on that app we have a session composed, which is an anonymous session by default, then when you invoke the authenticate transition on the app.session.authenticate, what's going to happen is your app is going to get replaced because it's going to be a new, it's going to be a mutable object. So you're going to get a new version of app, and on that app there's going to be a session property which is going to have, now instead of it being an anonymous session, it's going to be an authenticated session. And then because it's a different type, that now has different transitions. So you could do things like on an authenticated session, you can now log out. So before you didn't have log out because you were not authenticated, but now that that node has changed, you can actually do you can actually log out you can transition your application into the logout state by calling logout transition. And so this quality is really interesting because what this allows you to do is it allows you to build state machines. So if you've tracked state machines in JavaScript, there are a few tools that are available for doing this. The one thing that's kind of different is that Microstates tends to take a very holistic approach to this. So the mechanics of building state machines are like at the core of how Microstates is designed. So when you use Microstates to build state machines, you get a very expressive mechanism, very comprehensive mechanism for expressing state machines. There are some things that are really useful to know about transitions, because in Microstates, but in general, what you'll find is that there is behind the simplicity, we're hiding a lot of architectural decisions. So one of the things that one of the architectural decisions that we built into microstates from day one is that we don't force you into the into asynchronous paradigm. When you're working with microstates by default are synchronous. And they're also lazy, meaning that if you invoke a transition on a microstate, unless you've actually tried to read the state from the object that's created, that transition is not actually going to do anything. All you're doing is when you're invoking a transition, you're saying, I would like the next state to change in the following way, but that change will only happen when you actually read that state. And this is really interesting because if you think of what's happening right now with increasingly the frameworks that are being used to build JavaScript applications, they are moving towards async rendering engines. And what that does is that when the view layer becomes asynchronous, what happens is that it allows them to break up the computation of rendering the DOM over a few cycles. So you could do certain things that are important early on, and you could do more other things that are less important later on. And what Microstates does is it gives you a mechanism to like built into the microstate. Into Microstates, you have a mechanism to participate with these frameworks in a way that they're designed to work. So you actually, out of the box, you get the benefit of having your transitions be lazy, and so you can actually break up into the architecture is baked in the ability to break up computations to be split up over multiple render cycles. So what transitions do is transitions are declaration of how you want the state to change. And the result of that operation is going to be given to you when you actually perform the read on that microstate. And this applies to very complex trees. So what you could actually do is you could have you have a microstate that represents the entire state of your application, and you could render one part of the tree. So, for example, it's very common for us to think about our applications as being like JavaScript applications, like in React or Angular or Ember or Vue. They render trees of DOM, and depending on what you're doing with the application, it's going to render different parts of the DOM tree. And so what Microstates does is it allows you to do similar thing on the state level. So you can actually do, it gives you a way to think about your state in a similar paradigm. So far we've talked about types, which give us ability to reference paths in microstates, and it allows us to invoke transitions at specific places. And so what these things do is as I said earlier, Microstates takes a holistic approach to things. So one of the benefits of doing working Microstates, because it's immutable, it allows us to derive state in a way that can actually be cached. So you can actually, if you've researched memorization or if you use memorization in your applications, memorization is built right into microstates. So, and this has really important consequences in modern JavaScript frameworks, because what happens is most of the frameworks like React and like all these frameworks, most of them optimize based on if the value has changed. So if your reference has changed, it's going to know that it needs to re-render something. And so if a tool is designed to eliminate unnecessary recalculations, what it also does is it eliminates the necessity to create new objects when the state hasn't changed. So when you have immutable objects, you can actually cache the computations, the derived state, because that state will never change, because that object is immutable. And so there are two kinds of immutable state that is really helpful in applications. So one is two kinds of derived state. So one is a computation that results to a value. So if you think of, for example, like something simple like this, where you have a list of to-dos, and you might want to be able to say, whether or not the to-do has whether there's any items in the to-do. Like, one way, sorry, if there are any to-do items. So you could say like, does this, do I have to-do items? And so that would evaluate to true or false. So in this case, we really don't need memorization because it's pretty fast, but this is one kind of a value. You mean another one could be like, you could be computing, let's say you have a shopping cart, and in that shopping cart, you have a bunch of products, and you want to compute the total cost of all the products in the shopping cart, and let's say you have a bunch of them. So Microstates will automatically like memorize the total, so that if you read that total from the same shopping cart, if you read that total, it will only compute that once. It will only pay the cost of computing that one time. The other kind of, so that was an example of the computation computes to a value. Now another version of a derived state is when you want to reference objects, when you reference microstates inside of the tree. So that sounds really abstract, but if you want to, if you look at this example that I have here, if you were to represent your app, if you were to represent to-do MVC app as a microstate, what you would have is you'd have a bunch of to-dos, and depending on which filter you have selected, you might return a different collection of to-dos. So if you have things that are completed or active or all, depending on that, you would get different items. So filtered would evaluate to different things. Now, what's interesting here is that filtered property references microstate objects, which means that you can take that object and you can invoke transitions on it, and it's going to perform the right thing that you would expect it to do. And that could be really strange if you haven't used this before, but having the system just do the right thing for you is really powerful. So imagine in this case, like if you have a I'm not going to get into it. It's no, it's hard to. It's much easier to show visually, and I don't have a slide for that. So, but basically, if your query returns microstates, you're going to want to be able to change their state. But then when they return from a query, their path would look like it's different because it's actually coming like when you're working with to-do MVC, like to-do MVC dot filtered dot first dot completed dot set or toggle, and in that path, that node is actually like at path 1, but in the actual data structure it could be at path 10, and so you needed to do the right thing in that circumstance, and microstates will do the right thing for you. So the idea is that it should just do the right thing, whether you realize that it might be doing the right thing or not. Like, and it should just work for you. And then later you might see like, oh, it's actually doing the right thing. That's great. So far we talked about types and transitions and queries and questions. No? It's kind of, it's a lot of information. And I'm not saying that like, I'm saying that because it was a lot of information to put together in slides. So I know it's a lot of information. So we're doing a lot of things with microstates. So like one thing you could do is you could serialize a microstate to, you can take anywhere in the microstate, you can serialize that object by just accessing the state property, and it's going to give you a serializable version of that object. If you do it at the root, it will give you a serializable version of that entire state tree. If you do it at any of the particular nodes, it will give you the children underneath that node. So that's something Microstates does. It has it has this type system that as opposed to being compile time, it's in runtime. It's kind of similar to Mutable.js in that it has similar properties to it's immutable. It gives you ways to work with immutable objects. And how much time do I have? Okay. All right. I got 20 more slides. Okay. Okay. Cool. So another thing Microstates does is it uses lenses internally. So if you've never heard of lenses or you don't know how to use them, that's totally fine. But and so there's a lot of stuff going on, like lenses, like in Ramda, there's a tool called Ramda that provides lenses. So there's stuff that's inside, but the idea is that like all this complexity is abstracted over a simple API that you can use today and actually get benefit from. It has memorization with computations like you would get with reselect, or if you get with like, if you use view, you get computer properties, or with Ember, you get computer properties. So why do we do so much work? I mean, there's so many things that Microstates does. Like, why are we doing all of this? Because the reality is that writing applications is hard, and what we're doing is hard. But we want to do the hard thing now, so it'll be easy for you going forward. So you can actually, like, you can reap the benefits of the work that we've done, so to make your life easier. And the reality of the work that we do is that writing performant applications is actually really difficult. If you've ever experienced optimizing React, and I would assert that the challenges that you have optimizing React, they're similar challenges that you would have in other frameworks. They're just different challenges. They have a different, based on the architecture, they would have a different kind of collection of challenges that you have to deal with. And so the way you optimize performance in React is by reducing unnecessary re-renders. And if you want to eliminate unnecessary re-renders, the way you do that is by eliminate creating new references in your render hook. So because what happens is React can be really fast if nothing changes between renders. If you create new references, then React needs to know that, oh, actually, then React thinks that something has changed, and therefore it needs to re-render the components underneath that render. And making performant React applications is actually challenging. Even for a small application, it's actually challenging. And I can show you this because if you don't optimize a React application, it is quite likely that it's doing a lot of re-renders. And because our computer is so fast, we don't notice that. But there's a lot of problems, because what happens is that it starts off really simple, and then 6 months into it, you wrote a lot of code, and you're a week before you're going to go to production, and now your application is really slow. And because as a developer, you're not testing every possible permutation. Like your users will be interacting with every part of the app. You're only ever interacting with one part of the app. And so you might actually not realize that sometime into it, your application has actually become really slow and unresponsive, and you don't even know. And so if you wanted to see what's happening with re-renders in React, you can use the React DevTools, and what that will do is it will give you this option here, which is you can highlight updates. And what that will do is it will allow you to interact with your application, and it will show you which parts of the applications re-render. So what I'm going to show you is how different React applications re-render to do MVC app. And then notice the borders that show up around the components, and you will know which of the things are being re-rendered. So we're going to look at set state first. So look what happens. See that red? That means that those things are re-rendering. So that's to do MVC app with set state. So I think it's pretty safe to assume that this application has not been optimized, because you're going to be able to do MVC app. You're not going to spend some time like optimizing it to make it like really performant. And so that's what happens. Every time that you type something in, it's re-rendering the entire application. Now, if we look at the same thing with Redux, Redux is better, but you notice the list still gets re-rendered all the time. So depending on what part of the, depending on what you're doing, it's actually re-rendering different things, but it's fairly consistent. So imagine what would happen if this is not a simple application, but this is actually each one of the items in the list is actually a complex state tree, and then something like a table that has a lot of components in it. If each one of those things will be re-rendering, and your application is going to be super slow. Now let's look at MobX. MobX is doing something very similar. It's re-rendering the entire list. And depending on how the application is implemented, there could be slightly different properties. Like you will see different things being re-rendered. And so why I'm showing you this is that these tools, like ideally what would happen is you write the application and it just works. It doesn't need to be optimized. But that's not how it works. You write this application, and then you find out a week before you go to production that your application is actually slow, and then you spend a month delaying your go live because you need to fix stuff. And so what I would like to show you next is what happens with microstates. So microstates is not perfect, right? But what it does is by being able to by focusing on making all these things work well together, we're able to do what's happening here is you notice that none of the list items are being re-rendered. And I didn't have to optimize anything. This is just how Microstates works. And if you look at the red frame, so really what should be happening is when you type into that input field, the only thing that should be changing is the input field. That's the only thing that should be re-rendering. And with Microstates, that's not the case right now. But because of the way Microstates is written, because it's such a high-level tool, we can optimize internals. So if you start using Microstates today, you will actually, over time, see benefits from performance because you operate, when you program with Microstates, you operate at a higher level. It allows us to replace internals completely. And so I suspect that we will be able to optimize such that when you type into the input field, the only thing that changes is the input field. And that's the goal that we're going after. So, we've been working with Microstates for a while. We've been working towards a point like this point that we're at now for 2 years, and we've done presentations. We've rewritten Microstates 7 times, and all of that because we wanted to get to a point where we'll have stable external APIs. So like the way the user application is not going to change, so that we get to a point where even if the internals change, it'll just get better for you. You can start using Microstates today, and as the improvements come in, those improvements are going to be free for you. And so one of the other things that I'm really kind of proud of is that Microstates is only 5.5 kilobytes gzipped. And this is important because we want Microstates to be a tool that you reach for every time. It's not like a tool that can work for you under certain circumstances or when a project is big enough, you want to use Microstates. No, it's like I want it to be a tool that you're like, oh, I'm just going to use Microstates, and you eventually forget and you just use Microstates and just don't really use anything else. But I think that's possible. And the way you do that is it has to like hit the right markers. And so having a small library actually makes it possible for us to make it applicable in more use cases. To give you a kind of perspective on this, Redux by itself is 2.5 kilobytes. Redux with immutable JS is 20 kilobytes. So Microstates is 3 times smaller than immutable JS. I don't know, MobX is kind of hard to compare, but it seems to be really big. But for what it does, it's pretty tiny. It's smaller than Redux and Lambda.js lenses combined. So it's good size. We're proud of its size. And so you can start using Microstates. You can go to GitHub Microstates organization. You can see it there. It's still it's going to be an ongoing project. Like we're going to continue to work on it, but we're hoping that it's going to make your lives easier today.